In this video, we're going to talk about concavity. We could figure out how a graph looks, whether it's what's called concave up or whether it's concave down, based on the second derivative. When we talk about concave up, and I'm going to use CU for concave up. Concave up, think about it kind of like a bowl. If we were to pour water into this bowl, then, or this shape, then it would hold water. Concave up is always going to hold water. Concave down is going to be shaped differently, where it's not going to hold water. If we were to pour water on this, notice it would just kind of run off. Now, we can determine whether we're concave up or concave down by looking at the second derivative. If f double prime of x is positive, then we're going to be concave up. So we're going to look something like this. And if that second derivative is negative, then we're going to be concave down, which is going to look like this. So we could think about everything in relation to the graphs of f double prime of x, f prime of x, and the graph of y equals f of x. So to demonstrate what's going on this table, I'm just going to use a really simple example. One of those parent functions from 171 that we're all familiar with. Let's talk about y equals x squared. So we know what this graph looks like. This graph is open upward, looks like this. It's a quadratic. We know that this guy is concave up, but let me show you what this table is actually referring to here. So if we were to take that first derivative of x squared, we would get 2x. So notice 2x is a linear function. It's going to go through the origin, and it's always going to be increasing, so it's going to look like that. So notice that my f prime of x is always increasing here. If I look at my second derivative, which is a positive 2, this second derivative is always positive. And it's going to be this horizontal line, y equals 2. So you can see how that second derivative is positive, how these things are kind of relating here. We have a graph that's concave up. I'm going to start over here. That gave us a first derivative that was positive, and because it was concave up, that second derivative was positive. Likewise, if we were to look at a reflection of x squared, like negative x squared, we know what this looks like. It's a reflection about that x-axis. So this now opens down. This graph is concave down. If we were to look and analyze that first derivative, we would get a negative 2x. Now we have a negative slope, and the graph of that derivative would look like this. So it's always decreasing. We have something that's concave down. That derivative is going to be decreasing on that interval that it's concave down. And notice that second derivative is a negative 2, and negative 2 is always negative. If we were to look at that graph, it would be a horizontal line through y equals negative 2. So when we talk about this chart, you do have to be careful here. It's easy to misinterpret this. This is really talking about the graphs and how they're all relating in here. And it turns out we'll be able to use the first and second derivative and put those things together to graph functions, which we'll talk about in a couple of sections. So just some pictures. If we're concave up, we could look at like any one of these three functions. Notice what's happening with that graph here. In this case, looking at the graph, the derivative f prime of x would be negative because we would have negative slopes. Here, still a concave up, but we have negative slopes here, or horizontal slope here, and then positive slopes here. So that first derivative is going from negative to positive there. So we have some decreasing to increasing. And then we have f of x that's increasing, which means the first derivative is always positive, but this is going to be a concave up graph. So we could have all kind of different things happening to the graph in that first and second derivative. Same thing when we have something that's concave down. We could have something that's increasing the decreasing, or decreasing. The next thing we need to talk about is this idea of an inflection point. An inflection point is a place where the graph is going to change concavity. Now, it has to be a point in its domain. It can't be something that's not in the domain. So if we were to look at something maybe like y equals x cubed, you could see some concavity in that function, that parent function. You can see how this is concave down on this left-hand side, and then it's concave up over here. Well, we have a change in concavity at the origin in this case. So how do we know if we have an inflection point? Well, we really need to first create some kind of sign chart to go along with that. So we need to determine concavity. So here are your steps for figuring all of this stuff out. First thing you got to do is find that second derivative. And then you want to, just like with first derivative, find some partition numbers by setting that derivative equal to 0 and finding where the function's undefined. Then you're going to create a sign chart for the second derivative. Make sure you label this, because now we're going to have a sign chart for the first derivative and the second derivative. And then we're going to test the intervals. And then we're going to see where there's going to be a change in concavity. If it changes from a positive to a negative on that sign chart at some value, then that C value is where we have a change. But keep in mind that that number has to be in the domain of f of x. So let's do a few examples to make this a little bit more concrete. Let's say we want to find the inflection points of this cubic function. So we're going to start by finding that derivative. The first derivative is going to be 3x squared minus 18x plus 24. The second derivative is 6x minus 18. We're going to take that second derivative and we're going to set it equal to 0. And we're going to find partition numbers. So when we do that in this case, we're going to get x equals 3. So that is a possible inflection point. Now I'm going to abbreviate possible inflection point with PIP. We don't know if it's an inflection point until we put it on a graph. So this is where we're going to start testing things in that second derivative. And here's our second derivative. So let's plug in 0. If we plug 0 into that second derivative, we're going to have 6 times 0 minus 18. Well, that's just going to be a negative 18. So we're going to be negative here. Now let's plug in something bigger than 3, like 4. If we substitute in a 4, we have 6 times 4 minus 18. That's going to end up being a positive number. Once again, it doesn't matter whether we have what the number actually is. We just need to know, is it a positive or a negative? So we would say this graph is concave down from negative infinity to 3, and it would be concave up from 3 to infinity. So that means we do have an inflection point, and that's happening at x equals 3. So if we were to graph this function in our calculator, it would look like this. I just typed it into y equals there with a standard 10 by 10 window. And you can see how we're increasing, then we're decreasing, then increasing. Okay, when we talk about concavity, we're talking about the shape. So you can see how it's shaped kind of down here. That's what it means to be concave down. And then right here at x equals 3, we change from being shaped down to being shaped up. So we're concave up on this interval. Now, if we wanted to find that point, we need the y value. And we can find the y value just by plugging 3 into that function. And if I plug 3 into my function, I'm going to get a y value of 8. Remember, we always find y values by going back to the original function. So the point would be 3 and then 8. And we get that y coordinate by using the original function, finding f of 3, which in this case gave us 8. All right, so let's do another one. Let's look at this one. So we've got to find a few derivatives. So our first derivative is going to be negative e to the negative x times the derivative of the exponent, which is going to be, make that a positive e to the negative x. And then our second derivative of that is going to be e to the negative x times the derivative of the exponent, which is going to be a negative e to the negative x. So to talk about concavity, we need to know where this is equal to 0. So we have, and I'm going to rewrite this as negative 1 over e to the x, and that's going to be equal to 0. If we tried to solve that for x, we would multiply both sides by that e to the x, and notice that we would get something strange. Negative 1 is equal to 0, but we know that's not true. What that means is that there is no solution to this. So let's think about what's happening with that second derivative. We could rewrite that this way. And when we have that second derivative is negative 1 over e to the x. Well, e to any number is always going to be a positive. So I have negative 1 over a positive number. That's always negative. So this is one of those strange ones where when we set that second derivative equal to 0, there's no solution. There's also not a place where that derivative does not exist. So we have to think about, well, what's happening with that derivative? Can we figure out, is it always positive or always negative? And in this case, we can figure out it's always going to be negative. So since the second derivative is always less than 0, then that means we are going to be concave down. And it's going to be concave down on the entire domain of the original function. And the domain of the original function would be all real numbers. So we can confirm that just by looking at this in the calculator. So if we were to graph this one, there's our function, negative e to the negative x, and you can see how it's always going to be concave down, which verifies what we just found algebraically. So since this is always concave down, there's no change in concavity right there, okay? It's always concave down. So that means there's going to be no inflection point for this particular problem. To have an inflection point, there has to be a change in concavity, and this one just doesn't have any changes. Let's look at that second matched problem. It was g of x equals the ln of 1 over x. Now we could rewrite that as x to the negative 1 or negative 1 ln of x. So rewriting makes it easier to take the derivative. The derivative of the ln is 1 over x. And we could rewrite that as negative x to the negative 1. And then we need to take a second derivative. And we're going to have, when we bring that exponent down, now a positive 1 and subtract 1 from the exponent. So we're going to have x to the negative 2. So before we think about concavity for this problem, we really need to think about what is the domain of the original function. Well, we know there are some limitations with the ln. We know 1 over x has to be greater than 0, because when we take the ln of something, we can't take the ln of negatives or 0. Also note that x can't be equal to 0, because then that's going to be undefined. So where is 1 over x greater than 0? Well, if you think about what 1 over x looks like, it looks like this. And it's going to be positive here. So then the domain of that function would have to go from 0 to infinity. So now that we know the domain, we can start thinking about concavity. We've got the second derivative, and that's the same thing as 1 over x squared. To find possible inflection points, that's those partition numbers that the steps I laid out was talking about. You would start by setting that derivative equal to 0. But if we set that equal to 0, again, we have no solution for that. So then we ask ourselves, is there a place that's undefined? And yes, notice that it's undefined at x equals 0. So this is our partition number. What that does is it splits this number line for that second derivative into pieces. Now, we know the domain of the function is from 0 to infinity, so it doesn't even matter what's happening here because it's not going to be in the domain of the original function. So when I test, I really only have to test this interval. So let's pick something bigger than 0. I'm going to pick 1. This is going into the second derivative. I'm going to get a positive number out. I'm going to get 1. So what this means is this is always going to be concave up on its domain, and that's from 0 to infinity. So once again, we don't have any changes in concavity. We have just one thing that's happening here. And we could also verify this with the calculator and the graph if we wanted to.